Let's jump right into this explainer. Today, we're diving deep into the brilliant math of cause and effect. We're going to look at how modern researchers use two deeply complementary mathematical frameworks to figure out how our complex world actually works, translating real-world events into rigorous, actionable math.
Imagine, for a second, you're a public health researcher in Nairobi, Kenya. You've just wrapped up analyzing data from this massive BedNet distribution program across thousands of rural households. And you see a 23% drop in malaria mortality. That's a truly incredible, life-saving number, right?
But then, your supervisor walks in and asks a deceptively simple question. Did the bednets actually cause that drop in mortality? Answering that is remarkably difficult in practice, because proving true causation, that requires a highly rigorous mathematical language. And today, we're going to learn exactly how to speak it.
Here's our roadmap for getting there. 1. The fundamental problem. 2. Rubin's framework. 3. Pearl's framework. 4. The modern synthesis. And 5. Real-world applications. Let's get to it.
Section 1. The fundamental problem. Over the last century, statisticians and computer scientists have been building complementary paths up the exact same mountain. The roots trace all the way back to Jerzy Neyman in 1923, moving through Donald Rubin's vital work in 1974, Judea Pearl's foundational structural models in 2000, right up to the modern synthesis that epidemiologists rely on today. To climb that mountain, all of these researchers had to deal with counterfactuals. Basically, a counterfactual is just the hypothetical, unobservable outcome that would have happened if a different treatment had been applied. Think of it this way. Every individual unit, like a household, has two potential outcomes: mortality with a bednet and mortality without one. But the fundamental problem of causal inference is you can only ever observe one of them. The other, it's forever unobservable.
Section 2. Rubin's framework.
So, how do we estimate a causal effect from observational data? Well, Rubin's potential outcomes framework relies on three core assumptions. You can kind of think of these as the holy trinity of identification: exchangeability, positivity, and consistency. Let's unpack that first one, exchangeability. It essentially means that if our treated and untreated groups hypothetically swapped their treatments, they'd have identical average outcomes. In plain English, any differences we measure are strictly due to the intervention itself, not some underlying confounding factors like wealth, genetics, or healthcare access. The other two are absolutely crucial as well. Positivity means every single individual has a non-zero probability of receiving every treatment, meaning no one is completely excluded from the possibility of getting a bednet. Meanwhile, consistency demands a strictly well-defined intervention. Giving someone a bednet can't mean 12 completely different things across a single study. If these three assumptions hold, we can mathematically mimic a randomized experiment and cleanly isolate that true causal effect. Section 3. Pearl's framework. Now, Judea Pearl approached this exact same problem, but he used the highly visual language of artificial intelligence and structural models. His framework rests on three distinct pillars that make up structural causal models, or SCMs. We're talking about directed acyclic graphs, or DAGs, structural equations, and something called the do operator. Together, these pillars explicitly map out the exact data-generating mechanisms of the physical world. The do operator is really Pearl's signature mathematical contribution. It's a mathematical notation that represents a surgical, active intervention. You see, standard statistics relies on passive observation. We just condition on the data we happen to see. But the do operator mathematically severs incoming causal arrows to show exactly what happens when we step in and actively intervene. The second pillar, DAGs, are visual maps of this data-generating structure. They make all of our hidden assumptions perfectly visible. Because they map the structure out so clearly, DAGs easily reveal systemic phenomena like collider bias, which can completely skew your data if you ignore it. By drawing out this causal graph, researchers can use visual rules, like Pearl's famous backdoor criterion, to instantly trace pathways and know if a causal effect can actually be mathematically calculated from observational data. Section 4. The modern synthesis. At this point, we're really just looking at two dialects of the exact same logical language. On one side, we have Rubin's experimental design dialect, heavily relying on counterfactuals and exchangeability. On the other, we have Pearl's structural dialect, using DAGs and the backdoor criterion. And here's what's truly amazing. Rubin's core concept of exchangeability perfectly maps onto Pearl's backdoor criterion. They are parallel mathematical concepts.
Ultimately, These frameworks are mathematically equivalent. They're perfectly complementary paths leading to the exact same scientific goal. Today, modern epidemiologists actually use both fluently. They'll use Pearl's DAGs to visually map out their assumptions and identify confounding variables, and then they seamlessly switch over to Rubin's potential outcomes math to actually calculate the specific numerical estimates. It's a beautiful, true scientific synthesis.
Section 5. Real-world applications.
Let's look at 3 massive historical applications of causal inference. Whether it was using mathematical tools like Cornfield's inequality to definitively prove smoking causes lung cancer by ruling out hidden genetics, navigating super messy COVID-19 data where baseline assumptions were constantly violated, or transporting malaria data across the vast African continent, combining these tools ensures rigorous, life-saving results.
Let's jump back to our malaria example for a second. Researchers face massive challenges in the field. Take transportability, for instance. Calculating if a Kenyan bednet study mathematically applies to a completely different ecosystem like Mozambique. Or interference, measuring the spillover effects when bednets in one household actually reduce the mosquito population for their neighbors, which violates traditional isolated assumptions. To solve these really complex puzzles, researchers seamlessly integrate both Pearl's graphical diagrams and Rubin's counterfactual equations.
And the result of all this math? Over 663 million. That is the estimated number of malaria cases averted in Africa between 2000 and 2015. So this isn't just abstract math on a chalkboard. Using these complementary causal frameworks literally allowed public health officials and policymakers to make confident, targeted decisions that changed the world.
As the saying goes in the field, be a careful causal thinker who knows both languages and chooses the right tool for the question at hand. Causal inference begins exactly where standard statistics ends. It absolutely requires us to be multilingual problem solvers, combining our real-world domain knowledge with these incredibly rigorous mathematical structures.
So, I want to leave you with this final thought. Which high-stakes problem will you solve by mastering the dual lenses of causal inference? Thank you so much for tuning into this explainer. I really hope this empowers you to explicitly map your own assumptions, utilize the absolute best of both frameworks, and discover the true causes shaping our fascinating world.